In this section, we're looking at partial sums of arithmetic and geometric series. So let's consider an arithmetic series with 100 terms. So if its first term is 4, then if I want to compute the common difference, if I want to compute the 100th term, we can take that first term 4 and we can add a bunch of 3's to it. If it's the 100th term, we can add 99 of those, or one less than the term number. And that means that the 100th term is 4 plus 3 times 99, which is 301. And now we're going to write this series in expanded form. We're going to do this in a special way. We're going to show the first 3 and the last 3 terms explicitly. So the series starts with the first term 4, and then if the common difference is 3, the next term is 7, the next term is 10. We're leaving out some in the middle with that plus dot dot to indicate that not all terms are explicitly stated. And our last term is 301. The immediate preceding term is 298, and the preceding term to that is 295. Now what we're going to do is to take the same series, but write it backwards underneath. So 4 plus 7 plus 10 plus will be 295 plus 298 plus 301 on the left side. Now each pair of terms that are aligned vertically, we're going to add together. So first 4 plus 301 is 305. 7 plus 298 is also 305. In fact, if we add all terms that line up vertically, they all add up to 305. And now we just have a bunch of 305s that are added together. How many of them? Well, there were 100 terms, so there are 100 305s to add together. So those add up to 305 times 100, which is 30,500. Now if I want to find the sum of the original series, what we need to realize is that 305 plus 305 plus 305, etc., came from adding together the series with itself. So it's actually counted twice. And so if we just want one of those, we can take that 30,500 that we calculated and just divide it by 2, which will give us 15,250. All right, this suggests the sum formula for an arithmetic sequence. So if I want S sub n, which means I want the sum of n terms, that is n, the number of terms, times the first term plus the last term, over 2, where a sub 1 is the first term, a sub n is the nth or last term, and n is the term number of the last term, or the number of terms that we want to add together. So now let's put this to use. In example 1, we have an arithmetic series that has a first term of -2 and a common difference of 5. We're going to find the 88th partial sum of the series. Let's think about the things that we know and the things that we need to know in order to use this sum formula. We need to know n, the number of terms. Well, that's covered by the 88th partial sum. We want to know the sum of 88 terms, so n is 88. We also want to know what the first term is, a sub 1, and that is -2, so we already know that one. The only thing missing here is a sub n, which is the last term, which for this specific example is a sub 88. So we can use the idea of an arithmetic sequence to find the value of this. The first term plus the common difference times 1 less than the number of the term is equal to the 88th term. So let's compute that. -2 plus 5 times 87 is 433. So now the sum of 88 terms is n, the number of terms, which is 88, times a sub 1, which is -2, plus a sub 88, which is 433, all over 2. If you're computing that, suggest that you use control divide for a horizontal fraction bar. And then we'll just enter in 88 times -2 plus 433 divided by 2 gives us 18,964. All right, your turn to try the one below. Pause the video while you do this. The sum of this arithmetic series, or the sum of 52 of its terms anyway, should equal 52. All right, let's move on to example 2. This one has a different pattern of things that are given. The arithmetic series has a first term, so we do have that. That's 8. And the sixth term is 38. What we don't have is that common difference. And we want to find the sum of 40 terms. So we'll need to know the 40th term. In order to find that, we need the common difference. So first, let's relate the first term with the sixth term. Since there is a difference between their term numbers of 5 between 1 and 6, that means that we'll add 5 common differences to get from the first to the sixth term. So a sub 1 is 8. 8 plus 5d is equal to a sub 6, which is 38. So 5d is 30, which means that d is 6. From here, we can find the 40th, or the last term of the series, which will be the first term 8 plus the common difference 6 times 1 less than the number of terms, which will be 39. So computing that, 8 plus 6 times 39 is 242. And now we can use the sum formula. The sum formula for 40 terms is 40 times the first term, 8, plus the last term, 242, all divided by 2. Control divide on the calculator gives us that horizontal fraction bar. 40 times 8 plus 242, all divided by 2, is 5,000. All right, try the one below on your own. So in your original, it should say, I think, the 10th term is 11, but we need to change that to the 11th term. All right, try that one on your own. You should have gotten the partial sum of 554. By the way, the reason that we're calling these partial sums is that series can be considered to have an infinite number of terms. And so in those cases, when we compute the sum of 40 terms, we're only partially summing up the sequence. All right, let's take a look at example 3. Here we have a series that's given to us in expanded form. So we are going to first write it in sigma notation and then find the sum. So some quick observations. We know what the first term is, it's 3. We know what the common difference is, it's 4, because the next term is 7 and the next 11. So we can write a general formula for the nth term. We'll need that for our sigma notation. So in general, the nth term of an arithmetic sequence is the first term plus the common difference times 1 less than the number of the term. Let's clean that up just a little bit using the distributive property. So that's going to give us 4n minus 1. The other thing that we do not know is how many terms are actually in this sequence. We do know that the last term is 75, but we don't know what number term that is. So let's take our 75 and replace a sub n with it. Set that equal to 4n minus 1, and then solve. And that's going to give us 19. So there are 19 terms in this series. Now we were asked to write this in sigma form. So in sigma form, this is the sum as n goes from 1 to 19 terms of the formula for the terms 4n minus 1. So there's one of our answers. And then they also asked for us to compute the sum. So let's compute the sum of this series. The sum of 19 terms is equal to the number of terms times the first plus the last over 2. So I'm using control divide, 19 parentheses. It'll help if I type it right. 19 parentheses 3 plus 75 over 2 is 741. All right, you have one below to try on your own. Here's the sigma notation as well as the partial sum for this example. Let's move on to example 4. This is an arithmetic series that has a first term of 15, a common difference 4, and a sum of 3219. This time we're tasked with finding the number of terms in this series. So we do know that we can find a way to find the nth term. A sub n is the first term 15 plus the common difference 4 times 1 less than the number of terms. So this gives us 15 plus 4n minus 4, or 4n plus 11. Now, what we don't know is the number of terms. But the partial sum formula tells us that S sub n is n times a sub 1 plus a sub n over 2. So we know the sum is 3219. And we know a sub 1 is 15. We also know a sub n, which we just found the formula for, is 4n plus 11, divided by 2. So on the right side, we can do some simplification. We have n times 4n plus 26 over 2. Sorry, I'm squeezing that in to the space available. Let's go ahead and simplify that. So 3219 is equal to, and let's distribute both the n and the divided by 2 to both terms, 4n plus 26. So that'll give us 2n squared plus 26n. I'm sorry, plus 13n. Forgot to divide by 2 there. That's a quadratic equation. We can solve it by bringing that 3219 to the right side of the equation by subtracting it. And now this is probably factorable, but these numbers are way too big for us to worry about that. So we have a calculator. We're definitely going to use the quadratic formula on this one. So n equals the opposite of b plus or minus the square root of b squared minus 4 times a times c, and remember c is a negative number, so be sure to include that, and then all over 2 times a, which is 2. Alright, now I'm just going to use the calculator to compute those two values. Remember, the quadratic formula is giving you two values, one for plus and one for minus. So let's do the minus first. So control divide. That's going to give us negative 13 minus the square root of 13 squared. I'm going to watch my cursor, make sure that I'm in the right place as I enter these. 13 squared minus 4 times 2 times negative 3219 over, and I'll just go ahead and do the multiplication there. 2 times 2 is 4. Enter that. That's going to give us negative 87 halves. There's a couple things wrong with that answer. Number one, it's negative. The number of terms in the series should not be a negative number. Number two, it's fractional, and n is a counting number. Now that's okay, because we have two solutions. One of them will be the right one. So apparently the right one is when we use plus instead of minus. So let's go back to that same calculation, and let's just change that minus to plus. And that'll give us 37, which is the correct answer. We got two answers algebraically, but only one of them made sense in the context of the problem. All right, you can try the one below on your own. All right, for this one, we should have found that there are 51 terms in the series. I do want to point something out. This requires a little different method, since in this step right here that I just highlighted, those numbers 33 and 19 are not divisible by 2, so instead I multiplied both sides of the equation by 2 to clear that fraction. All right, now let's move on to geometric series. So for geometric series, we're going to consider a particular geometric series with a first term of 3 and a common ratio r. If we calculate the 100th term of this, that's the first term times a bunch of r's. And so we'll multiply by 1 less than the term number, that number of r's, which is r times r times r times r, etc., or r to the 99th. So now what we're going to do is write an expression for the sum of 100 terms. And we're going to show the first 3 terms of the series. The first term is 3. The second term is 3 times r. And the third term is 3 times r squared. Now I'll include the ellipsis. And then the last term, which is the one that we just computed, 3 times r to the 99th power. Right underneath it, I'm going to write an expression for r times the sum of 100 terms. So if the first term is 3, the first term in this series will be 3 times r. And I'm going to write it underneath the 3 times r in the other series. And so all of the terms will just have one additional factor of r in them. And to get to the 100th term of this series, we'll have to include a 3r to the 100th. Now I want you to notice that all the like terms again are adding up or aligned vertically. And what we're going to do on the next line is we're going to do a subtraction. So we're going to take that top line s sub 100 and subtract r times s sub 100 from it. So we're taking the top and subtracting the bottom. So 3 minus 0 is 3. Now take a look at the next set of terms that lines up. 3r minus 3r is 0. 3r squared minus 3r squared is 0. And in fact, we're going to have terms that line up that way all the way through 3r to the 99th power. Now let's look at that last pair of terms that line up. There's really a 0 in the top series. And then minus 3r to the 100th power is 3r to the 100th power. Now let's take and factor the left side into s sub 100 times 1 minus r times s sub 100. Just realized that there was an equal sign above there, should have been a subtraction. All right, and then we can factor the right as well. 3 factors out, and that leaves us with 1 minus r to the 100th power. So solving for s sub 100, we can divide. That gives us 3 times 1 minus r to the 100th power over 1 minus r. And that suggests a partial sum formula for geometric series, which is s sub n equals a sub 1, the first term, times 1 minus r raised to the nth power over 1 minus r, where again a sub 1 is the first term, r is the common ratio, and n is the number of term number for the last term. So in example 5, we have a geometric series with a first term, 128, so we can use that in the formula for the sum, and a common ratio of -1/2. So we're trying to find s sub 10. So s sub 10 equals the first term, 128, times 1 minus the common ratio, -1/2, raised to the n power. And if we're finding s sub 10, that means that n is 10, all divided by 1 minus the common ratio. Be really careful with two things here. when we have a ratio that is either negative or fractional, and this one is both, we need to make sure that we include parentheses around that number raised to a power. Otherwise, your calculator will not understand what it is that you mean for it to do. So we have to think about order of operations here. That power needs to happen first before the subtraction. Do not change it to 1 plus 1/2 to the 10th power. All right, we're going to let the calculator do the rest of the heavy lifting here. And so enter control divide for a fraction 128 times parentheses 1 minus, and then we'll have to put an additional set of parentheses inside that other parentheses, negative 1/2. Now take your cursor and move it outside the parentheses, that is outside the negative 1/2 parentheses, but inside the other, and raise that to the 10th power. And then downstairs we have 1 minus negative 1/2. And if you want to save yourself a keystroke there, you can write 1 plus 3/2. And that's going to give us a sum of looks like 1023 over 20. And you can also take and write this in decimal form if you want to. Sometimes it might be easier just to copy down the decimal value. So press Control and Enter, and that'll give you the decimal value, which is 51.15. All right, you have one to try on your own. This is geometric series with the first term of 81, common ratio of 2/3. Find the 8th partial sum. All right, this one for you to try. The sum should either be as a fraction 6305 over 27 or as a decimal 233.519. Either one is okay. Just FYI, I keyed in the previous example's computation incorrectly, so the corrected numbers are above there. All right, let's move on. In the next example, 6, we have a geometric sequence that has a first term of 2/27, and it has a sixth term of 18. So we're going to have to figure out what that common ratio is. Well, we know in a geometric sequence that if I take the first term and I multiply it by r raised to the 5th power, that's going to give me the 6th term. So 2/27 times r raised to the 5th is equal to 18. We can solve this equation by multiplying both sides by 27/2. And so let's go ahead and do that. So the calculator do that computation. So 18 times 27/2 is 243. So it looks like r to the 5th power is equal to 243, and r will be the 5th root of 243. There are a couple different ways you can key that into your calculator. To get the 5th root, Control and the caret key will allow you to fill in the index of the radical. 5th root of 243 is 3. There's a second way that you can key this in as well. This one might be easier if you like fractional exponents. The 5th root is the same as raising 243 to the 1/5 power. So that gives us 3. So we found the common ratio is 3. Now, I think we have everything that we need to find the partial sum. So S sub 9 is the first term, 2/27, times 1 minus the ratio, which is 3, raised to the 9th power, over 1 minus 3. If you want, you can insert parentheses around that 3, but it's not necessary since the 3 is neither fractional nor negative. All right, let's let the calculator do that computation for us. So I need a horizontal fraction bar. In the numerator we have 2/27 times 1 minus 3 raised to the 9th power, and then in the denominator 1 minus 3 is 19,682/27. Or, as a decimal, Control Enter, 728.963. Either one is fine. All right, I'm going to change this next. Try this. There's a little complication in here. Let's actually make this 3 plus 3 halves plus 3 quarters plus 3 eighths, all pluses, all the way up to 2048ths, and put it in sigma notation and then find the sum. All right, for this one we should have found that there are 12 terms by setting the last term 3 over 2048 equal to the general formula 3 times 1/2 raised to the n minus 1 power for the nth term. And there we get our sigma notation, and using the sum formula you can either have a fractional value or you can just use a decimal value if that's easier for you. All right, last example here. How many terms of this geometric series must be added for the sum to exceed the number 4.9? So for this one, this is an infinite series, but we just need to know how many terms do you need to make it to 4.9 as a sum. All right, so our first term is 1, and our ratio is 4/5. So the sum of n terms is the first term, which is 1, times 1 minus the ratio 4/5 raised to the n minus 1 power. Sorry, that is to the nth power, all over 1 minus the ratio, which is 4/5. We're going to replace the nth partial sum with 4.9, and now we just have 1 minus 4/5 to the n power over 1 minus 4/5, which is 1/5. So we'll do a little simplification. Now we can clear the fraction by multiplying by 1/5. So 4.9 times 1/5 is equal to 1 minus 4/5 raised to the n power. Let's figure out what 4.9 times 1/5 is. Is 0.98. Now, you might want to just subtract 1, but then we're going to have to divide by a negative, so I'm going to just suggest that we take that 4/5 to the n and we move it to the left side of the equation where it'll become a positive term, and then we move the 0.98 to the right side where it'll become negative. So now we have 4/5 raised to the n power is equal to 0.02. That's an exponential equation, so we can use logarithms to find the exponent n. So n is equal to the log base 4/5 of 0.02. So log is control and then the 10 to the x button. We have to enter the base 4/5 and then use the right arrow key to get inside the argument of that logarithm and enter in 0.02. That gives us 17.53. And remember, n is a counting number, right? So do we actually have a number of terms where the sum adds up to exactly 4.9? No. But what we know is if we add only 17 terms, we won't quite get there. So we're going to need to add 18 terms in order for that sum to first exceed 4.9. And that's it for this lesson.